for being there with me. I'm glad to have you. Today I want us to look at motion, the concept of motion. What is motion? That is the first question we'll ask ourselves. Motion is nothing but a change in the position of an object, or we can say motion is a change in the orientation of an object with respect to time. Now, this motion of an object can be caused by a factor called force. So force can cause the motion of an object to change. Now, if a body is at rest, that body will continue to be at rest today. It's only force that can cause it to start moving. Now, if the body is in motion with an unchanged speed or with constant speed, it is as well this force that will bring it to a halt. So, force is an important factor in the concept of motion. Now we'll now look at the causes of the types of force later in a later video, but not in this video. Now we'll look at the types of motion we have. There are basically about 4 types of motion. Now we have the first type, which is the translational motion. We have the second one, rotational motion. Now the third one, we have oscillatory. We have oscillatory motion, or we can say call it vibrational motion. The fourth one, we can have random motion, random motion. Now we take these concepts one after the other. Translational motion. Translational motion is a type of motion or the movement of a body along a straight line with unchanged speed, or along a curve without rotating. Now, when a body moves from one point to another, maybe along a straight line, we have translational motion. There are several examples of translational motion. For example, if a car moves from one particular position to another, what we have is a translational motion. It can be along a curve, but the fact that I want us to pick here is that it doesn't rotate. It can move along a curve, but without rotating. Now, another example we can have here is an airplane moving from one station to another along a straight line. It could as well be a curve. Then there are other examples too. We can have kicked football. If you give a football a kick, it moves from one point to another along a straight line, and then by landing, it can now give us a curve. Now we can have the flow of river. River always flow in a straight path, or it can be crooked path. However, it must not rotate. Now we still have the movement of glacier and all the rest of them. So once we have a movement along a straight line, what we have is translational motion. Number 2, we have rotational motion. By this rotational motion, we mean the motion of a body around a fixed point. For example, if we have the motion of the ceiling fan, a ceiling fan moves or rotates about a fixed point. It must have a fixed point. Another example we can have here is the motion of the tire of the car. Remember, the motion of a car and the motion of a tire are two different things. The motion of a car, straight line, it is translational. Now, the motion of the wheel of that car is rotational because it has a fixed point. Now, most times we can, in fact, this rotational motion, most times we can call it a circular motion. It must be motion around a curve, but it must have a central point. The difference between circular motion and rotational motion is that for circular motion, it has a constant radius from the center. If here is the center, we can have from here to here is a constant radius. For example, this same fan too, the rotation of the ceiling fan is rotational motion, while the blade itself moves around a circular path. Of course, it has an equal radius from each center. Apart from that, circular motion and rotational motion are the same thing. Now, there are other examples of circular motion or rotational motion. We can have even the motion of a merry-go-round. Merry-go-round sweeps circular motion or undergo rotational motion. Motion of a compact disc or DVD player. That DVD rotates round. Of course, it must have a central focus. So these are more some of the examples of rotational motion. We can still have the electric motor, we have generators, all of them under rotational motion. Now, we'll talk of the oscillatory motion or vibrational motion. This is a type of motion of a body that goes either back and forth, to and fro, or up and down about a mean point. It has a fixed point or equilibrium point. For example, we can have the motion of the pendulum clock. If you notice the pendulum clock, it keeps moving to and fro about a fixed point. But most times, there are situations where vibratory motion does not have a fixed point. For example, the beating of the heart. It's always to and fro without having a fixed point. Now, there are other examples of oscillatory motion. Let me read it here. To have a plucked guitar, the moment you pluck a guitar string, it vibrates up and down. We have like I said, pendulum clock. We have the swing sets. The swing sets undergo oscillatory motion. We have the motion of vibrating mass on a spiral spring. If you load a spiral spring, you have it will be oscillating up and down. Vibration of prongs of a tuning fork. A tuning fork, once you break a tuning fork, it strikes the tuning fork. The prongs keep vibrating to and fro. So these are some of the examples of vibratory motion. Another one is random motion. For random motion, it has unpredictable movement. You cannot predict the movement, the motion at any point in time. For example, the motion of a butterfly. When you think the butterfly is moving left, the next thing it will move back, or it will move to the right. The motion is highly unpredictable. You cannot predict the motion of a random motion. Now, like we said, the motion is irregular. The manner on which it moves is irregular. Another example is the Brownian motion. Now, the smoke in the air, if smoke in the air is moving, you cannot determine the exact motion it is taking. Another example of if I have a smoke particle suspended in the air, just like we said, when you suspend smoke particles or even dust particles, once you suspend them in the air, you may not be able, you cannot even determine the direction on which they are taken at any point in time. Now, we'll now look at some of the example, we now look at the equations of motion. Now, the equations of motion we have are, so now look at equations of uniformly accelerated motion. Uniformly accelerated motion. There are basically about 4 equations of a uniformly accelerated motion. We have the first one, of course, it stems from acceleration, which is v is equal to, a is equal to v minus u all over t. And of course, if you cross multiply, make v the subject, we now have that v is equal to u plus at. So that is the first equation, number 1. Now, number 2, we have the one that says v squared is equal to u squared plus 2as. This is the second one. Now we have the one that says s is equal to ut plus half at squared. Half at squared. We also have the one that says s is equal to average speed, which is u plus v all over 2. Average speed multiplied by time. Most times we do not make use of this one. So these are the equations of uniformly accelerated motion. Now we define each of these terms one after the other. We have our v, we have u, we have a, we have s, we have our t there. Now v is the final speed. V is the final speed or final velocity. Final velocity measured in meters per second. U is the initial velocity measured in meters per second. A is the acceleration. A is the acceleration of the body measured in meters per second squared. Now we have t. T is time measured in seconds. S is distance. S is a distance, or it can be a displacement measured in meters. Having explained all these things, when I look at conditions to use each of these, because most times students get confused as to when to use each of these equations. Now, for the first one, we have v. Now, those conditions are, number 1, if a body starts from rest, or if a body accelerates from rest, that means initial velocity is 0. Point number 1. If a body accelerates from rest or starts moving from rest, the initial velocity is 0. Now, point number 2. If a body comes to rest, final velocity becomes v is 0. If a body comes to rest, the final velocity becomes 0. That means we'll now take care of the initial velocity. Now, the third one is if a body is moving at constant speed, or if the speed of a body is unchanged throughout the journey, that means there is no acceleration. Acceleration becomes 0. Let us repeat what we have just said. If a body starts moving from rest, u is 0. If a body comes to rest, the final velocity becomes 0. If a body is moving at a constant speed without changing the speed or without changing the velocity, acceleration becomes 0. Now let us take some calculations to be able to understand this problem. I'll leave these equations and okay. Now we take the first question. The first question says a particle accelerates uniformly from rest at 6 meters per second squared for 8 seconds and then decelerates uniformly to rest in the next 5 seconds. Determine the magnitude of the acceleration. Determine the magnitude of the acceleration. Now, just before we start, acceleration and retardation are the same. Acceleration, and either you call it retardation or you call it deceleration. Deceleration. This is the negative of this. Acceleration means increase in speed, while retardation is decrease in speed. Acceleration has positive sign, while retardation or deceleration has a negative sign. So as we move on, we will now consider that. So from the question that they gave us, they said a particle accelerates uniformly from rest. Now, since it's from rest, solution. Since it's from rest, u is 0. Now, they gave us the acceleration there. Acceleration is 6 meters per second squared. Time taken there, time is 8 seconds. Now, remember, the body accelerates up to a particular speed. And then from there, it starts deceleration. Now, the question says, determine the magnitude of its deceleration. So, deceleration now, I want us to look at it. Deceleration is what we are looking for. However, from here, they gave us V, U to be 0, A to be this, and T to be this. Now, before we start calculating the deceleration, the body also accelerated to a certain speed. Now, since it accelerated to a certain speed, we must find that speed. From that speed, it is from that speed that it starts decelerating. Now, since it accelerated from accelerated to a certain speed, let us find the acceleration there, the final velocity there. Now, we said that V is equal to U plus AT. V, we need to find V. V is equal to, U is 0 plus A. A is 6 times T. T is 8. Now, we bring our calculator. V is equal to, of course, here is 0. 6 times 8. 6 times 8 will give us 48 meters per second. Now, this is the velocity from which it started decelerating. Now, at this point now, we can now calculate our deceleration. Remember, it started decelerating from here. This V now would be our initial velocity, because it started from the question where asked to calculate the deceleration. Since the body has not stopped yet, this velocity, this value of velocity becomes our initial velocity now. Therefore, we now have that U becomes 48 meters per second. V at this point, because it has not stopped, becomes 0. T is 5 seconds from the question. Now, we need to calculate the deceleration, which is the A. Deceleration and the acceleration are expressed as A. So in other words, we still make use of this same equation. V is equal to U plus AT. Now, V, like we said, is 0 now because the body is still in motion, it has not stopped. Is equal to U. That velocity attained from which it started decelerating becomes our this, which is 48 plus a, which is what we are looking for, times t. T is 5. It will now give us, of course, if we send this one here, it becomes minus 48 is equal to this one here, 5 times a, 5 a. Now, a will give us minus 48 over 5. Therefore, deceleration there, which is the negative acceleration, will give us 9.6 meters per second squared. So, this is the value of the retardation of that body. Please, the first thing is to understand the question. Once ability to understand the question will give you a leeway to solving the problem. Now let us look at another problem. Question number 2. The number 2 says, a body accelerates uniformly from rest at the rate of 3 meters per second square for 8 seconds. Calculate the distance covered by the body during acceleration. Now, with solution, we have a body accelerates uniformly from rest. Since it is accelerating uniformly from rest, u becomes 0. At the rate of, that means our acceleration is 3 meters per second squared for 8 seconds. Time is 8 seconds. Calculate the distance covered during the acceleration. Now, distance covered. Having listed all these things now, we'll now look at which of these equations will satisfy this. If you look at the first one has no s. Second one has, this one has v, but here we don't have v. Now the third one, which is a ut plus half at squared, this one, of course, this one doesn't have v. This one is the most suitable for the equation. We have, so we make use of this. So we now have s is equal to ut plus half at squared. Now s is what we're looking for. S is equal to u. U is 0 times t, 8, plus half times a. A is 3 times t, t squared. T is 8, which is 8 squared. And 8 squared will give us s equals here 0 times 8, of course, is 0, plus half times 3 times 8 squared is 64. Now we now have 64 times 3, 64 times 3, 192 times half will give us 96. Therefore, s is equal to 96 meters. So this is the distance covered during the journey. Now we'll take the next one, but before that, we'll clean the budge so that all we'll be solving will be on this side of the budge. The third question says, a body uniformly accelerates from rest at 8 meters per second squared. Uniformly accelerates from rest at 8 meters. That means acceleration is 8 meters per second squared. In how much time will the body travel a distance of 2.5 kilometers? In how much time will the body travel a distance of 2.5 kilometers? So this is a distance, 2.5 kilometers. Okay. Now we have A, this, and we're looking for T. So a body acceleration uniformly from rest at 8 meters per second squared. In how much time will the body travel a distance of 2.5 kilometers? Now looking at this, and of course this one is in meters, this one is in kilometer. What do? We convert it. Kilo means 1,000. So multiply this by 1,000. 2.5 times 1,000. Therefore, distance traveled will give us 2,500 meters. Okay, now we ask ourselves the first question: which of these equations will satisfy A, T, S? Remember, it starts from rest. Since it started from rest, U is 0. And of course, it is this same equation that will take care of this problem. So we now have S is equal to UT plus half AT squared. S is, of course, we use the converted value instead of 2.5. We use a 2,500 is equal to U. U is 0 times T plus half times A. A is 8 times T. T is unknown, which is square. We now have 2,500 is equal to, of course, this one will now give us a 0. We have half times 8, which is 4. 4 times T squared will give us a 4T squared. Now we'll make T squared the subject from here. We have T squared is equal to 2,500 all over 4 will give us 2,500 divided by 4 will give us a 625. Therefore, T is the square. Since this is T square is equal to, we're looking for T and not T square. So T, we divide both sides by, we take the square root of both sides. 625, and the square root of 625 will give us 25. Therefore, T is 25 seconds. Alright, we'll take the next one. This one very important. Now this question says, a motorist traveling at 120 km per hour sees a broken down truck at the middle of the road and immediately applies his brakes and comes to a stop with a uniform retardation in 20 seconds. What distance does the car travel after the brakes were applied? What distance does the car travel after the brakes were applied? So we take a look at this problem. Now we said that yes, a motorist traveling at, now since he's traveling at, it didn't start from rest. That is initial velocity. So initial velocity U is 120 km/h. And of course, the first thing we'll do is to convert this straight away, kilo. Of course, we now have 120 times 1,000 km all over hour. 60 seconds times 60 minutes make 1 hour. So we now have 60 by 60. All which will give us that U is equal to 1,200 all over 3,600. So by the time we do the necessary calculation, we have 1,200 divided by 1,200 divided by 36. And if we do that division, we now have that our U is 33.3 meters per second. Okay, we continue. A motor is traveling at this, sees a broken down truck at the middle of the road, and immediately applies his brakes and come to a stop with uniform retardation in 20 seconds. T is 20 seconds. What distance does the car travel after the brakes were applied? So, in other words, we now have that V is 0 and U. This is the values we have. This is U, value for U. This is T. That is V. Now we have that the car traveled with at a point. We have the retardation. See, they said here, what distance does the car travel after the brakes was applied? Now, when the brake was applied, the car came to rest. Now, the first thing we need to do is to calculate that retardation. Retardation is not there. How do you calculate the retardation? And it's after calculating the retardation that we will not be able to calculate the distance covered. So these are the two things we are looking at. The retardation first, and we have the speed. For the retardation, of course, we have V to be 0. This is U, this is T, and A. The only equation that will satisfy that is this one, V. So we now have V is equal to U plus AT. 0 is equal to U, 3.3 plus A times T. T is 20, which will now give us 0 is equal to 3.3 plus 20A. Now, we move this to this side to now become minus 33.3 is equal to 20A. Now, the retardation now, A is minus 33.3 all over 20. Therefore, retardation or the deceleration will now give us 33.3 divided by 20. Will now give us minus 1.67 meters per second square. Having gotten the value of the retardation, the next thing now to get is the distance covered the moment the brakes were applied. Now, how do we get this distance covered? If you look at this now, we have U, we have T, we have V, we have A, and we have S. This equation has S, U, A, and T. This one also has a U, A, sorry, okay. The second question, please. The second equation has S there. It has acceleration. So, there are some problems that will require you to use. Any of the equations can solve, yes. For this one now, each of these two equations can solve this particular problem. Now we now have, so what we are looking for now is our distance covered. Therefore, distance covered after the brakes were applied. We now have S is equal to UT plus half AT squared. Using this, we now have S will substitute S equals U. U is 3.3 times T. T is 20 plus half into A. A, of course, A is minus 1.7. Minus 1.67 multiplied by 20t, 20 squared. So, which will now give us 33 point, so we have 33.3 times 20 will give us S is equal to 666.6. Now, if you open this bracket, half times this will now give us minus half times 1.67 times 20 squared is 400. 20 squared is 400. So we have S is equal to 66. Okay, let's take 666.6 minus, we'll take the first one, 1.67 times 400 times half will give us 334. So S is equal to 666.6 minus 334 will give us 332.6 meters. And of course, this is the final answer. Please help me use this second equation. Use this one. V is equal to V squared is equal to U squared plus 2AS. Please help me find out if the two are the same. If this one, with this, if you're able to get 332.6 meters. So if you're able to get this value with this equation, please let me know in the comment section. Thank you for joining us, and thank you for your patience for being here with us. I hope to see you in the next video, where we'll now deal with how we can use graph to solve this equation. But if this lesson was helpful to you, please give it a thumbs up, turn on the notification button, and share this video with your friends. Thank you very much.